Hello students, in this video lecture I am going to discuss how to solve Cauchy problem for a first order quasi-linear partial differential equation when the Cauchy conditions or the initial conditions are given in parametric form. Now in my earlier video I have already discussed how to solve Cauchy problem for a first order quasi-linear partial differential equation, but in that video we had taken the Cauchy conditions to be conditions in Cartesian form. In this particular video, we are going to solve Cauchy problem for a first order quasi-linear partial differential equation, but the initial conditions or the Cauchy conditions will be in parametric form. So the question is how to tackle such type of Cauchy problems. Now let me consider a question in this regard. We have to solve, the question says that you have to find out the solution of the equation ux plus uy is equal to 1, which I have marked as 1, for the initial data xs0 is equal to s and y at s0 is equal to 2s and u at s0 is equal to s, where s is a parameter. Here u is a dependent variable u is dependent on the independent variables x and y. So, x and y are the two independent variables that we have in this problem. Also this particular equation which we have marked as 1, this is a first order equation because first order partial derivatives ux and uy are occurring in this equation 1. Ux is del u by del x, that is the first order partial derivative of u with respect to x, and uy is the first order partial derivative of u with respect to y, del u by del y. So, equation 1 therefore becomes a first order equation. Also equation 1 is quasi-linear because as I have already discussed in my earlier videos, a quasi-linear equation always looks somewhat like this: aux plus buy is equal to c, where a, which is the coefficient of ux, b, which is the coefficient of uy, and c, which refers to the terms on the right hand side of the equation. All these can involve x, y, and u. They can have just the variables x, y, and u. They are functions of x, y, and u, and we can see that this particular equation, which we have marked as 1, in this case the coefficient of ux, the coefficient of uy, and the term on the right hand side, they are very much satisfying this particular condition, which is the condition for the equation to be a quasi-linear equation, that the coefficients can involve only the coefficients a here is u, the coefficient b, which is the coefficient of uy, which is 1, and c, which is 1 over here. So the coefficients can involve terms involving x, y, and u. So they are very much satisfying this particular equation. So this is very much a quasi-linear partial differential equation of first order, and we know how to solve this type of equation. We have already done a method regarding that. In my earlier video, I have already explained that if you are given a first order quasi-linear partial differential equation of this type, then you can use Lagrange's method or the method of characteristics for solving it. So, but the point is that in this particular problem, you are not only given the equation, but you are also given the initial data or the initial conditions, and these conditions are given in parametric form where s is a parameter. So, of course, we have to apply Lagrange's method only or the method of characteristics, but there is a particular way in which Lagrange's method will be applied, which is going to be different from the way that I mentioned when in my video when the initial conditions were in Cartesian form. Here the initial conditions are in parametric form. Now you can just see that x, if you take a look at x, the variable x, the variable y, and the variable u, then you can just see that x, apart from having the variable s is of course a variable over here, and s is only the term of s is coming on the right hand side. Apart from the variable s, it is written s x s0, which means that there is a other variable also which comes over here. There is a other parameter also which comes at the second position. So this is the second position where the other parameter comes. Now this if you compare this whole thing, let me just erase this so as to make space for some rough work. Now if you just compare this whole question with the article that I discussed theoretically, then in that article if you go and have a look at that video, then we had seen that the initial curve c that in parametric form can be written as x is equal to x naught t and y is equal to y naught t, and the initial data which is the value of u, was given in the form of u is equal to u naught t. So this is how we had represented the initial curve and the initial data, where t was a parameter. The only difference in this particular question is that instead of t, the parameter that is mentioned here is s. So these conditions are just these conditions which are given in this form: x as 0 is equal to s, y as 0 is equal to 2s, and u as 0 is equal to s. They are actually conditions which are similar to this. The only difference is that instead of the parameter t, parameter s is given. That is the only change. And so this actually, this instead of writing this as x naught t, you can just refer to this s as x naught s, where s is a parameter. This 2s can be referred to as y naught s, where again s is a parameter, and this s can be referred to as u naught s. So this is one thing. Then again this second position, as I was already referring, the second position this is also there, which means that there is another parameter on which x, y and u are dependent. So basically let me call that the other parameter as t, because one parameter is s, which we have seen, and the other parameter is t. So basically you have that x is actually a function of s and t, where s and t are both parameters. Y is a function of s and t, where s and t are parameters, and u is also a function of s and t, where s and t are the two parameters. So this is the case. So in this case, the second parameter t, the second parameter t comes from the characteristic equations that occur in the Lagrange's method in parametric form. So because this is a first order quasi-linear partial differential equation, so of course we are going to use Lagrange's method for solving it. And till now the characteristic equations that occur in the Lagrange's method that we have been using, those equations we have been using in Cartesian form. Now for this particular question, because there are two parameters which are involved, one parameter is s, which is occurring over here, and the other parameter at the second position is t, which comes from the parameter which occurs in the characteristic equations, if you consider characteristic equations in parametric form. So whenever the Cauchy conditions or the initial conditions are given in parametric form, then the characteristic equations that occur in Lagrange's method, they also have to be considered in parametric form. And let me just recall, when you are given a first order quasi-linear partial differential equation of this type, aux plus buy is equal to c, then the characteristic equations in parametric form are dx by dt is equal to a, dy by dt is equal to b, and du by dt is equal to c, where t is a parameter. So this is the form of the characteristic equations in parametric form, and this form of characteristic equations we have already discussed when I was discussing Lagrange's method or method of characteristics for solving first order quasi-linear partial differential equations. Now here the characteristic equations are therefore dx by dt is equal to a is the coefficient of ux, which in this case is u, then dy by dt is equal to b is the coefficient of uy, which is 1 in this case, and du by dt is equal to c is whatever you have on the right hand side. On the right hand side we have 1. So these are the characteristic equations in parametric form, which we are marking as 2. And t is a parameter, and you have to remember that in this case x will be a function of the two parameters s and t. S was already occurring in the Cauchy conditions, and t is the parameter which comes in the characteristic equations. Y is also a function of s and t, and u is also a function of s and t. Now what we do is we solve the initial conditions that are given to us. This was already given to us in the question, or the Cauchy conditions were given to us in the question, that x as 0 is equal to s, y as 0 is equal to 2s, u as 0 is equal to s. We are just calling the first in the first condition, the right hand side we are denoting as x naught s, and this we are denoting by y naught s, this we are denoting by u naught s, the way we have done in the article. The only difference is that in the article, as I was already in this particular lecture only, I have just told you that the initial conditions we wrote the initial conditions in the form x is equal to x naught t, y is equal to y naught t, and the initial data was in the form u is equal to u naught t, where t is a parameter. The only difference in this question is that instead of t, the parameter which is occurring in the question is s, that is the only difference, and the parameter, the other second parameter t which comes, that comes from the characteristic equations. So now with these three initial conditions which we have marked as 3, 4 and 5, now what we do is we consider the third equation first in the characteristic equations 2. Characteristic equations have been marked as 2, and we consider the third equation in the characteristic equations 2, which means that I consider this one, du by dt is equal to 1. So consider the third equation in the characteristic equations 2, that is du by dt is equal to 1, this one, and I just integrate with respect to t, because I know that u is a function of s and t. So I just integrate this whole thing with respect to t. So on integrating with respect to t, on the left hand side we get u, and u is equal to t plus constant of integration, and writing explicitly u as a function of s and t. So u s t is equal to t plus constant. I mark this as 6. I use the initial condition 5. The initial condition 5 was this one, us 0 is equal to s. This is the initial condition 5. So I can write the initial condition 5 over here. The initial condition is us 0 is equal to s is equal to u naught s. I use this initial condition. So over here, so for using this particular initial condition, you need to put t is equal to 0. Wherever t comes, you have to put t is equal to 0. So I put t is equal to 0 over here, and this us 0 stands for u naught s. It is u naught s. I write u naught s as it is. T on the right hand side becomes 0 plus constant. So just this expression we don't need now. So the value of the arbitrary constant comes out to be u naught s. So this we have marked. Now using this value of the arbitrary constant, using 7 and 6, we have ust, this is as it is, ust as it is from here is equal to t plus this constant. This constant, the value of this constant is u naught s. So we have put the value of the arbitrary constant as u naught s. So this is the relation that we have. This is the expression that we have for ust, that ust comes out to be t plus u naught s. This is the relation that we have, and I have marked this relation as star, where u naught s in this particular question is s. This is the initial data that we have in this question. So from question to question, the initial data will change, but for this particular question u naught s is s. Otherwise, this is the general expression that you get over here. Then coming to the second equation of the characteristic equations 2. Now the characteristic equations 2 were written over here, and now I consider the second equation in the characteristic equations 2, which means that I am considering dy by dt is equal to 1. So just considering dy by dt is equal to 1. So dy by dt is equal to 1, where of course we know that y is a function of s and t, where s and t are two parameters, and now integrating this equation with respect to t, we get y is equal to, just integrating this one with respect to t, we get y is equal to t plus constant. Constant is the constant of integration, and now explicitly writing y as a function of s and t is equal to t plus constant, I mark this as 8. And now using the initial condition 4, the initial condition 4 was the condition that was given in the question already, that ys0 is equal to 2s is equal to y naught s. So I use this initial condition, that this is the initial condition 4. The initial condition 4 is that ys0 is equal to 2s is equal to y naught s. This condition I make use of. Now to make use of this particular condition, I have to put the second parameter t as 0. So wherever it occurs, so put the second parameter t as 0. So when you put the second parameter t as 0, here you get y as 0 and t is equal to 0. So t is equal to 0 comes over here plus constant. And now I don't need these terms. So the value of the constant simply comes out to be y naught s, and this we mark as 9. Now using this value of arbitrary constant, which is given in 9 over here, I put the value of the constant from 9 in 8. So using 9 in 8, yst comes out to be t plus y naught s. This is the value of the arbitrary constant. So this is another relation that we have, which another expression that we get, which we are marking as star dash, which gives you an expression for yst. Here of course in this particular question y naught s stands for 2s. So then now considering the last equation in the characteristic equations 2, which is the first equation which we haven't considered so far, which is dx by dt is equal to u. And again dx by dt is equal to u, this is the first equation of the characteristic equations, and here before you integrate we put the value of u, and the value of u we have already calculated in star, because star was an equation which was giving you the expression for UST or u. So, the value of u is by star is given by t plus u naught s. So, I just put the value of this value of u over here at this point. So, using this value of u in the above equation, we have dx by dt is equal to the value of u is t plus u naught s, and of course, we know that x is a function of s and t. So, integrating this equation with respect to t, we have on the left hand side we have x, and the integral of t with respect to t is t square by 2 plus u naught s into t plus constant, this is the constant of integration, and writing x explicitly as x st, that is a function of s and t, is equal to t square by 2 plus u naught s plus t plus constant. We mark this as 10, and now using the initial condition 3, the initial condition 3 was x s 0 is equal to s is equal to x naught s, this was given in the question. For using this initial condition, you have to put t as 0 wherever it comes. So, t, I will put 0 over here, I will put t as 0 over here, and I will put t 0 over here. So, this is what you have x s 0, here it should be x s 0, x s 0, x s 0 is same as x naught s, this is equal to 0 square by 2 plus u naught s into 0 plus a constant, and now you do not need these mid expressions. So, the value of the arbitrary constant comes out to be x naught s, and now using the value of this arbitrary constant at this point, just substituting the value of the constant from 11 in 10, we get the value of x s t. X s t comes out to be t square by 2 plus u naught s t plus the value of arbitrary constant is x naught s, where we know that u naught s stands for s in this question and x naught s stands for s in this question. So, this particular expression, which is an expression for x s t, I am marking this expression as star double dash. So, there are 3 expressions that you have from star, star dash and star double dash. These 3 expressions give you the value of the 3 variables u, y and x as in terms of the parameters s and t. This was the first expression that we obtained for u, ust is equal to t plus u naught s. This was the second expression that we obtained, yst is equal to t plus y naught s, and this is the third expression that we obtained, xst is equal to t square by 2 plus u naught s into t plus x naught s, where in this particular question we know that u naught s, y naught s and x naught s is equal to s. Now, here I have purposely kept u naught s as u naught s, y naught s as y naught s and x naught s as x naught s, although we know their values. But this is the way you have to proceed in every question. Although in this particular case, let me go back to the beginning. In this particular case, this s refers to x naught s, this particular 2s refers to y naught s, and this particular s refers to u naught s. But in different question it might be different. So, this expression will vary from question to question, but in any case the right hand side, this will always stand for x naught s, this right hand side will stand for y naught s, and this right hand side will stand for u naught s. Again here the second parameter t, here the second parameter t has been taken as 0, t is equal to 0 in the initial conditions, but again from the value of t, which is 0 in this case in the initial data, in the initial condition, that can also be different, t can be 1, t can be 2, but you have to proceed exactly in the same way, no matter what is the value of x naught s, y naught s, u naught s, or what is the value, the initial value of t, the procedure has to be same in all the questions. So, this is the way one has to proceed when the Cauchy conditions are given in parametric form. And now coming to the point where we have actually reached, we have reached this point where we have 3 expressions giving the values of the 3 variables u, y and x in terms of the parameters s and t. And now let me put the value of u naught s, y naught s and x naught s and u naught s in the in this context, in this particular question, these are the values. So, and let me write, instead of UST, let me write UST as simply U, and YST as simply Y, and XST as simply X. Although we know that U, Y and X, all these three are functions of the variables, are functions of the parameters S and T. So, we know that. So, but let me simply write the equations in simple form. So, I am writing U as U, I am writing Y as Y, and I am writing X as T as X. Also, this is the value, these are the initial conditions. I am putting the value of U naught S, Y naught S, U naught S and X naught S. So, these are the final equations that you have after putting the initial values. So, now these are the three expressions that you have, three equations that you have, 12, 13 and 14, and you just have to actually eliminate the parameters or the unknowns S and T from these three equations, and you will get a relation involving X, Y and U. So, that relation which you get involving X, Y and U after eliminating S and T, this relation will actually be the Cauchy solution of the given Cauchy problem. So, so basically we are now just going to eliminate S and T, the unknowns S and T from 12, 13 and 14. So, elimination process can be done in any manner. This is how I have done, but whatever strikes to you that you have to do, the point is you just have to eliminate the two unknowns S and T to get a relation between the variables X, Y and U, and that relation will actually be the Cauchy solution to the given Cauchy problem. So, from equation 12 we find out the value of S by bringing t on this side. So, S is equal to U minus t. So, this is the value of S, and then once you get the value of S, you substitute the value of S in 13 here at this point. The value has to be substituted, and when you make the substitution, y is equal to t plus 2s. This is the value of S that I have substituted, U minus t. So, y comes out to be 2u minus t, this is the value of y, or t comes out to be, you just bring minus t on this side and bring y on this side. So, the value of t comes out to be 2u minus y. So, this is the value of t and this is the value of S. And now you have to use these two values of S and T, which we have calculated in 15 and 16 in this X, which is t square by 2 plus St plus S. So, I use it over here. X is equal to 2u minus y whole square. This is the value of t that I have substituted, t square by 2 plus here it was St. So, this is the value of S, and this is the value of t, and plus S, this is the value of S. And then again t is again occurring at these 2 points, t is occurring at these 2 points. So, again I substitute the value of t here, this value of t has been substituted over here, and the value of t has been substituted over here. So, finally, this is the equation that you have in which S and T are not coming, and you just have to solve this equation to get the solution in simplified form. So, X is equal to 2u minus y whole square plus this is going to be y minus u. This expression comes out to be y minus u into 2u minus y plus y minus u. If you want to solve it further, you can solve it further, or you can leave it at this point. So, this relation which we have obtained in the end, this is the unique Cauchy solution to the given Cauchy problem. So, this is how the Cauchy problem has to be solved when the initial conditions are given in parametric form, the way they were given in this particular question. The initial conditions were in parametric form. Whenever the initial conditions are in parametric form in terms of the variable S, say, then you have to take the characteristic equations in Lagrange's method in parametric form, and the parameter can be taken as t, and then you have to proceed exactly in the same way, the way I have done in this particular question. So, that is all about Cauchy problem for a first order quasi-linear partial differential equation when the Cauchy conditions or the initial conditions are in parametric form.